very much. The floor is yours.
Thank you. Thank you. That's the plan, but I'm not sure it's going to work. I'm freshly jumped off. But, okay. So, thank you for having me here. And I think the quiz was a great intro to this talk. So I'm going to focus on dark energy and the concept of the expansion of the universe, and in particular how the expansion of the universe has been behaving in the last 5 billion years or so. And what the recent data that we have about this have been telling us, because it's a question that we've been having for a long time, and now it might be something that has been puzzling us, and the puzzle might have gotten just even more interesting. So who goes, you move the slides?
Click right here.
Oh, great. Yes. Okay, good. So, first of all, let me just, for those that are not very familiar with this, let me just show the universe in a simple schematic, with a simple schematic image, and point out a few things, in particular those that are relevant for this talk. So these are the very early times. That's when everything begins, and we have, of course, a lot of unknowns about that, but that's what we call the Big Bang, right? There's a beginning in time, and this is a very hot status of the universe. Everything is very dense, the universe is highly energetic, and it undergoes a phase of very, very, very rapid expansion. Okay? Then, soon after, it starts cooling down, and especially because it expands, starts cooling down, and the expansion starts also slowing down. And that's because structures start to form. And in a very simple terms, we can think that gravity, that there's matter out there, right? There's been some initial kick, but then there's matter right out there. Matter attracts each other through gravity. So there's some sort of gravitational pull that counteracts this expansion, which should be slowing down. And that's what we have been kind of observing after a very rapid phase of initial expansion. Although this is a straight line, so you don't appreciate it in this plot, the expansion has been kind of slowing down, and then somewhat it has started to speed up again. Okay, and that has been happening more or less around the last 5 billion years, around here. Now, before I get more into details about that, let me make a few things, set some common grounds. So what do I mean when I say early universe? What do I mean when I say late universe, and so on? Because I mostly work with the late universe, but of course it's all interconnected, right? I mean, we are here because there was an early universe, because there were some fluctuations in the early universe. If it was homogeneous, we wouldn't be here. So it's, and we are just the natural evolution of what was the early universe. But still, there's some things from the physics point of view and from the observations point of view that we can focus on, that are more relevant for the late times, and then there's a gray zone, depending on the taste and whatever, what we call late or early. So last few billion years, redshift 10 or lower, we can safely call it late universe. Very early on, redshift 1000 and more, very high energies, very high temperature, and you're gradually going into regimes where quantum physics is relevant. And instead, as you evolve towards the right, you're gradually going to lower temperatures, more sparser universe, and the regimes where classical physics is more relevant, right? So now in this talk, I want to mention and focus on 3 observations that we use in cosmology, and in particular 3 observations that are very relevant for making any conclusions about what we call dark energy. And I'll say a bit more, of course, also about what is it that we call dark energy, right? So, but before, let me flesh out what are these observations. Cosmic microwave background. This is like the picture of the baby universe. This is, you have a very hot and energetic plasma in the early universe. It glows. It emits radiation. And that's the radiation that we see. It's a sort of leftover. It's like you could take a picture at that time when the universe was really hot. And so when we measure the photons that reach us from the cosmic microwave background, we see the universe as it was some 14 billion years ago. Then there's more late universe type of probes. I'll talk about baryon acoustic oscillations. I'll try to explain in very few simple words what those are. And some others that you're probably familiar with, which are the supernovae. Explosions of stars that we use as standard candles to understand how distances change in the universe. So these are the three pillars that I'm going to try to use to learn about dark energy. Now, let me start with the cosmic microwave background. So it is one of the key evidences of this model called the hot Big Bang, the fact that the universe started from a very hot and dense status. At some point in time, everywhere, in every point in space, there was this Big Bang, and this very hot and dense plasma was glowing in some radiation, which we are observing now today, reaching us from any direction in the sky in which we look, right? So we look around us and we see photons reaching us from 13 billion years ago. And one thing that we can do, we like to say, is that we measure the temperature of these photons. It's just somewhat a way of measuring some properties, in particular the intensity with which they reach you, and how this intensity changes as a function of the wavelength of the radiation that hit your instrument, right? So out of that you can read the temperature, and then you can map it all over around you on a sphere, right? And it will be hotter in some positions, slightly colder in others, but it's a pretty homogeneous temperature. This difference is a very, very tiny fluctuation of 1 part in 100,000. But still, as I said, they better are there, right? Otherwise, we wouldn't be here. So these are pretty nice images. They have not as nice as and amazing as the simulation that Matthew showed, but still, it's, if you think that you're looking at the primordial universe, it's quite exciting. But that's not the information we want to take out. What we like to do as physicists and cosmologists and astronomers is to get, let's see if this is working. Yes. To get the so-called angular power spectrum out of this. So this is, don't mind too much what is written down here. Look at the angular scale on the top. So it's like you're looking at 2 points in the sky separated by a given angle, and you measure the difference in the temperature, right? And then you keep going, and you keep going, and you keep going. You look at different angles, and basically it tells you the intensity, the fluctuations in temperature as a function of the angular separation of 2 points. Okay? And there's a characteristic scale, angular scale, where these fluctuations are pretty big, and then they're very small here, and then smaller, of course, on smaller scales, but still with some oscillations. And now I cannot really enter too much into the details of this, or what this really means. We call it a power spectrum. But what I want to point out is that we are able to make theoretical predictions for what this should look like. So basically we are making predictions for what the temperature of the photons in the different directions in the sky should be. And we can measure it. So prediction is the purple line, and the measurements are the white dots, right? And we are kind of spot on with our theoretical prediction. So that's one way of understanding if our theory works well. And that's why we have learned a lot from the cosmic microwave background. It has basically, until now, it has been the one observable, the queen, I would say, of cosmology, the one observable that has basically put the seal on what we call the standard model of cosmology. We have been able, by measuring the temperature of this photon and looking how it changes as a function of angular separation, we have been able to tell with good precision that the universe is spatially flat, very nearly spatially flat. Of course, we never measure a number being exactly 0. There's some error bar. But that's one property that we have learned about the universe. We have learned also that it behaves very closely to what Einstein told us it should be doing, right? It behaves, it evolves according to the laws of general relativity, so the gravity as described by Einstein. And we have also learned, though, as you've seen in the quiz, that most of what is out there in the universe is something that we don't know, we are not familiar with. Only 5% of the universe is composed of normal matter, so whatever atoms and things you are familiar with and you can think of and have been detected somewhere, right? The remaining 95% needs to be made up in part by dark matter, and that's the thing that is crucial, for instance, for the simulation that Matthew has shown, is crucial for galaxies to form. Otherwise, we don't have enough mass to create the gravitational pull that you need to create the structure that we observe. But the large part of the current universe, around 70% energy budget of the universe right now, is in the form of dark energy. What is dark energy? Well, we know it's there. It's something because basically we count, we see what ingredients we need. We know that we have normal matter. We know we need dark matter to give the clustering, and we need something to explain how the expansion goes, right? And we call this something dark energy. And that's the only way in which we see it. We don't see it in any other way. We haven't detected it. And we don't even see it gravitationally in the sense in which we see dark matter, right? We know that it's an energy that should be there, and it's kind of sourcing the acceleration of the expansion of the universe at late times. Actually, the cosmic microwave background is one way of establishing that you need dark energy, but of course, the first way in which it was established experimentally, to the point that the Nobel Prize was given, was through the supernova. Now, let me, before I keep going, let's say a bit more about the dark energy. Let's see if this works. Let's try. I'm not sure it's going to work. So I just want to show you that indeed, yeah, the cosmic microwave background, but now you will probably have to move the cursors, right? So in the quiz, so this is the power spectrum of the cosmic microwave background, right? That tells you basically the fluctuations as a function of the angular separation on the sky. There, the black dots are data. You should think of those as measurements. The blue curve is something that you control. And you control it by creating your theory and using it to make prediction of what the temperature should be. Now, typically, the ingredients that you put in your theory are how much normal matter you need to have, how much dark matter you need to have, and how much dark energy you need to have, right? So, I'm not sure I wanted to quiz you on how much of those you should have, but maybe you can just go to the right pointers, because there was already in the quiz, and actually it's gonna save me some time, because I'm always very slow. So let's try and put dark energy to roughly 72. This is WMAP, so don't get too impressed. Then there's baryonic. I think we should go to 5% down there. all right? And then this should sum to 100%. So if you have 100% filled up the universe, you have also spatially flat universe. This is the pie chart that you saw in the quiz. And now you are not doing that well with your curve, right? You're doing quite well on the smaller angular scales on the right side, but if you look at the left side, you're pretty off. Now the reason is that as you see there's an extra cursor down there, which tells you the theory of gravity. So in this simulation is a big word for this. Not simulation at the point of the type of what Matthew showed, but in this interactive tool, you can change also the theory of gravity. So you say, well, maybe Einstein wasn't exactly correct, maybe it's not exactly GR, let me change it a little bit. And so here you have a cursor, and it's changing, you can try and move it. One of them, it gets even worse. Of course, we have chosen models that do pretty poorly to make it more dramatic, right? And you can see that most of these models do pretty poorly on the large scales. Those scales are typically very generous with you. The error bars are very large, but still you can screw up big time with your theory. I think if you go, it's counterintuitive, but I think that should be, hopefully, yeah, I think that's the best fit, given the spread of the data. So that should be the GR case, okay? I could still make a similar exercise with models that are modified gravity, but that can give a slightly better, perhaps, fit than this. But anyhow, okay, thank you. This was just to make the point that the cosmic microwave background is very sensitive to what is out there, but also to the theory that we use to describe our universe. Okay? So we need dark matter, we need dark energy, we need probably general relativity, although I like to also use alternatives to that. And then, let me skip this slide, I'll get back to it. I want to first get to dark energy, because I keep saying dark energy, so I just want to say a few more words. So what is it? It's this thing that we needed to introduce to explain the fact that the universe at some point started to accelerate, in the sense that the expansion, instead of slowing down under the effect of gravity, started to speed up. So a very simplistic analogy is think of throwing a ball up. You just give it an initial push, so you throw it with some initial velocity, and then just because of gravity, you expect it to eventually fall back down, right? But if there's dark energy somewhere there that enters into play, your ball might just take off, okay? So it might just start speeding up and taking off instead of slowing down and falling down back. So it's very counterintuitive type of energy. What we know, it's, we don't know what it is, of course, but we have kind of measured its properties. We can draw a profile, we can profile dark energy. And we can say that today, it is the dominant component. It's everywhere out there in the universe. It's what has been speeding up the expansion. It is very closely homogeneously distributed, and the property I like the most is that it is everlasting. That's the most counterintuitive for us. What does it mean? It means that as this universe expands, distances stretches, the volume stretches, the density of this dark energy, the energy density, remains constant. So if you think of a box with a number of particles inside with some mass, then you can calculate density, right? You divide the mass by the volume. If you then keep the same number of particles with the same mass and you double the volume, the density will happen, right? And it's like that works for matter with mass. It works slightly differently for radiation, but still you would have a behavior along those lines. Dark energy doesn't matter as how much you stretch, you expand and you stretch your volume, the density remains the same. Okay, so that's something that it makes it very difficult for us to explain and to understand what it could be. Except that maybe we have a good candidate, and this good candidate is the cosmological constant. So actually, Dutch physicist who got his PhD in physics in Leiden, Henry Casimir, actually showed with an experiment that empty space is not truly empty, and we rather call it vacuum, right? Quantum physics tell us that the vacuum is kind of populated continuously by particles coming into light, out of light, and so on, right? So it comes with its own energy. It's like the 0 point, if you've ever heard about oscillators, harmonic oscillators in quantum mechanics. It's like the 0 energy of the harmonic oscillator, 0 level, right? It's not 0. So there is some vacuum energy. So even empty space has it. But then Einstein told us that any type of energy gravitates, right? And not only told us that, but he told us also that you could add very easily a constant to its equation, to the beautiful equation that Matthew showed. There was a constant in there in the whole formula, without making anybody worry about. So you could kind of sneak in a constant, and there you go. You have your cosmological constant that happens to have the property of being mimicking an energy with constant density. Okay. So we have two candidates. We have this constant that you could just draw there, write it down, and choose a number for it. Classically, you could do it. From the quantum point of view, there's some issues. And then vacuum energy. Quantum mechanics, quantum field theory, whatever, gives you plenty of energy out of the vacuum. And it behaves exactly as you need, because more space you create, it's like you create also more vacuum, and the vacuum comes with its own energy. So it doesn't dilute away, right? So there you go. You have a candidate. The only problem is that this candidate that we have from theory is enormously bigger, way, way, way bigger than what we measure, in the sense that from calculating how the rate of expansion of the universe, we can also understand what this dark energy should be. And we can say we measure a given lambda, and it's way, 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 way smaller, embarrassingly smaller than what theory gives us. So it's a puzzling problem that has been keeping cosmologists busy for many years, for decades actually, since 1998, when the accelerated expansion of the universe was measured. So now sorry for doing this, I'm gonna go back for a moment. So I say 1998, how did we detect the accelerated expansion of the universe? That was through supernovae, right? These are explosions, very bright events that can happen in a galaxy, and for a moment when they happen, they can outglow the whole galaxy, basically, right? We like to think of them as standard candles. If a supernova happens here, at some point, somewhere in space, and at some moment in time, it emits radiation that will eventually reach you, right? But in between the emission and the time the radiation reaches you, the universe has been expanding, kind of working against this radiation that is trying to reach you. And so the radiation loses energy, it reshifts, okay? So then if you have another supernova that is somewhat closer, it will undergo the same phenomenon, it will just be reshifted a bit less, okay? If these were just the same exact bulb, like you think that you have a light bulb, which you know because you bought it, you know the lumen, you know exactly how bright it's supposed to be. And then if you see it dimmer and dimmer, you can understand that it's farther and farther away from you, right? So in principle, if these objects, these supernovae, are standard in the sense that they have the same intrinsic luminosity, if we measure the amount of luminosity, the amount of radiation that reaches us, then we can infer how distant they are. And more than that, we can infer how the universe has been behaving in between the time the radiation was emitted and the time we observe it. And that's what people have been doing. In 1998, that's how they first noticed that a universe that was just expanding slower and slower wasn't really fitting the supernovae. Supernovae want, and they still want, this is recent data from the Dark Energy Survey, they want a universe that is speeding up. The expansion is speeding up. Okay? So I should also go a little speeding up. I don't have an idea of the time. But let me go now to, so we need dark energy. It has these strange properties. We have a candidate from theory, which we don't fully understand, but it has one property. So the one property that you have to remember about the cosmological constant, and what we kind of measure, but with not so much precision about dark energy, is that the energy density is constant. Okay? So can we use new data to learn more about this dark energy? Is it really a cosmological constant? Is it really something with a constant energy density? Could it be something else? And of course the answer is yes, we can. There's a new experiment out there. We like to call them stage 4, galaxy and weak lensing surveys. So it's big surveys with telescopes either on the ground or in space that are mapping millions and billions of galaxies, measuring their positions and measuring their shapes. And that gives us a lot of information about the theory of gravity. Now, one that created quite a buzz is, if you want, the first out of this series of stage 4 surveys, which is DESI. DESI stands for Dark Energy Spectroscopic Instrument. In 2024, they released some interesting results on the nature of dark energy. But before I show you those results, and many of you know them, let me mention how they obtained those results. So they did so using the so-called baryon acoustic oscillation. You remember at the beginning I mentioned cosmic microwave background, supernova, LA times, and I said also baryon acoustic oscillation. What are these things? They are another phase of this oscillation that you observe in the power spectrum of the cosmic microwave background. Okay? So I've said that at the beginning you have this hot plasma which is glowing, but it's also plasma made of highly energetic massive particles and photons. They're kind of clumped together and they undergo rarefaction and compression, and this creates sound waves. Okay, we call it acoustic oscillations. They leave important imprints in the cosmic microwave background, and that's what the pattern that we see in the temperature. But that same pattern leaves also imprints in the distribution of galaxies as a kind of preferred scale for clustering. Okay? This is exaggerated. This would be very easy if that was the case, right? But this is showing that in principle there is a preferred length scale over which you have clustering around the central overdensity. Of course, that's, if you look at the, let me go to the next slide. If you look at the distribution of galaxies, and these are the actual galaxies that DESI has measured, roughly 40 million galaxies, you don't see those circles, right? You have to be really, to have really good analysis method to read that out, but that information is somehow in there. So you can still pick up this characteristic scale. They have a way of compressing this data, analyzing it in such a way of reading at different distances from us. They call it look-back time, how far back in time we look. They detect this characteristic clustering scale. Okay? And the fact that this scale was imprinted at birth, the scale was in, I'm almost done, I swear, but not yet. It was imprinted at birth, right? But then it lives as a fossil that evolves together with the universe and gives a preferred landscape, but you see it expands with the universe. So if we are able at every redshift, at any moment in time to measure this preferred scale, we can also measure how the universe has been expanding. So this is what DESI did, and this is what they are telling us about dark energy. So if it was really a cosmological constant, if it was really an energy that has a constant density, that does not evolve in time, it would be this straight white line, okay? This is time. Here we are today. Redshift is an analogous of time, right? The further back you look in time, the more the radiation had to travel to reach you, the more it was stretched and redshifted. So redshift, higher redshift mean further back in time. So this is the energy density of radiation. It would be roughly 70% if it was the cosmological constant. And this is a way of telling you what the data. Now, if you follow the central line, the brighter purple line, that's on average what the data measures, then of course there's always some uncertainty, right? But you do see that there are points where it really departs from being constant. And interestingly, it does it in a very funny, in the most possible interesting way. Because it doesn't stay above this value, it doesn't stay below, but it crosses it. And that has so many physical implications. I mean, we couldn't have hoped for a better outcome. So I like to think that that's Einstein say, haha, I told you. But that's also me when I saw these results, because I was like, yes, now we have work to do. It might go away, yeah? It's preliminary results, of course. We need more experiments. Okay, so wrapping up, we need more experiments, and next comes Euclid. I couldn't finish this talk without mentioning Euclid, of course. Many of us here are involved in Euclid. The Netherlands in general plays a very key role in Euclid, which is this European mission, this telescope that we've launched into space 3 years ago. Has been taking data since then. It will map basically the whole visible sky, so of course we have to stay away from where the galaxy is, and measure billions, the position and the shape for shape and photometry, yes, for billions of galaxies, and the precise position for 30 million galaxies. Okay, and this is a real example. This is real data. These are real images out of a patch here on the sky, and you can zoom in up to 60 times into these images. And there you go. This is the type of image that you need for cosmology, right? So I think Euclid will effectively allow us, at least that's the way I like to think of Euclid, it will allow us to play ball with the universe, because it's looking at positions of galaxies, the way they cluster, the way they grow into these filaments and so on. So that's very important for particles that have matter, that are massive, dark matter, right? But there's also the other aspects. It tells you how light is bended. Light that comes from further galaxies and come to you, but finds structure in between. It's bended, that's a prediction of general relativity. And if you compare the two, it's a little bit like comparing if a light and a very massive ball fall at the same rate or at a different rate. So that's why I'm saying I think of Euclid as playing ball just in the universe. So first results should come out at the end of this year if we work hard enough. So I would say stay tuned, and for the rest, I stop here and thank you for your attention.
So I think we still have a few minutes for questions, if there are any. Well, perhaps I didn't see any hands yet, so perhaps I'll get us started. So, what do you think the most exciting ideas to explain then why this dark energy may not be completely constant with time might be?
It's an interaction between dark energy and dark matter. So it's an exchange of energy between the two. That's at least this peculiar behavior that we are seeing right now. Because it has an energy density. Yeah, the way its energy density behaves, it first grows and then decays again. So the models we've been able to fit the best, and the sort of physics that we think is playing a role there is an interaction between the two dark components. Yeah. Or a theory of gravity that, yeah.
Is the response you would see in the dark matter then that you could actually use to test that idea further?
Sorry?
Is there a response you'd see in the dark matter with the size of halos or something change with time?
Yeah, probably there are aspects that you could check. Exactly, we haven't worked out exactly yet what, because these are very preliminary results, right? But if the type of theories that we think are behind this, then you would expect to see, for instance, features on the boundaries of clusters, for instance, and things like that, right? The spectral radius is a typical thing when you look at.
More questions? I see some hands. We'll start with one from the balcony so it doesn't get missed.
Maybe you can explain more what you meant by dark energy being everlasting.
Yeah.
One aspect I imagined was that maybe dark energy existed even before we started measuring Big Bang.
Dark energy?
Existed even before the Big Bang?
No, sorry, I mean everlasting in the sense, well, so I don't want to go to before the Big Bang because we don't know. So I really meant in the sense of, for the times we know, so from Big Bang on, it's there and it has a constant energy density, a very low one. So at the beginning, your universe is very dense in radiation and then in matter. Dark energy is there, but it has a very low density, so you don't see it. Then as the universe expands, radiation and matter dilute away, and eventually dark energy starts dominating. To me, that's an easier property to understand than, say, negative pressure or anti-gravity. But might be a matter also of taste.
There's one towards the back, and then we'll have the one at the front, and then we'll probably have to call it time.
Yeah, so on the graphical results, if you go near the larger redshifts, you saw that, I guess, the error region is quite big.
Yeah.
Is there any way to reduce that?
Yes, thank you for the question. So there's two things. So for sure, here, it's a matter also of the experiment, right? So DESI, the results of DESI that are used in this plot were mostly up to 1 point something, at most 1.5 or 4 even, okay? So there's some other data, the cosmic microwave background, but the cosmic microwave background is kind of out there. It's also sensitive to what happens here. So Euclid, it will go to higher redshift, so it will help to shrink some of these. But then you have also to think that eventually dark energy starts being less dominant than matter. As you go to higher redshift, dark matter becomes the dominant component. So it's harder to measure the density of dark energy. This is the density of dark energy. So there is an intrinsic limitation, I think. So somewhere in the intermediate region, the experiment can help you. Here, there's a bit of an intrinsic limitation, and then you have to be smarter and try to think of something else.
Thank you. Yeah, in this graph as well. So when it is above the horizontal line, that will tell us that the universe is expanding because of direct energy?
So, yeah, so this line, it's not so easy to read it out of this. There will be an analogous plot that I could show, but it has a similar crossing. So in this region, what happens is really that dark energy is behaving more similarly to, so you see, sorry, maybe what we can read off is here, its energy density is increasing, okay? So constant, which is something that was already a bit puzzling, increasing even harder, then it starts decreasing. So in this region it behaves like matter, like normal or dark matter, like something that we understand. And that's something that would give you a slowing down of the expansion. So we could think that maybe it's a speeding up in this region, but then it's a slowing down in there. Yeah. So it's not a constant simple answer.
Okay, thank you very much.